Welcome everyone. My name is Ihor Dvoritsky. I am a developer advocate at the Cloud Native Computing Foundation. And today we have our regular CNCF webinars that are happening every Tuesday exactly this time. And today we have the special guest, Kesh Sajjadi, who will present about moving to Kubernetes and share some insights on solving configuration, security, and collaboration challenges in the container pipeline. Kesh, let's go ahead.
Thank you very much. Hi, everyone. My name is Cash from Cloud 66, and today I wanted to share our story when it comes to moving our monolithic application that used to run on AWS to Kubernetes, and the challenges we had to overcome, the problems that we had to solve, and the surprises that we stumbled upon on the way of this move, where we are now, and where we think we will be moving our stack. So I'm going to assume that everyone is quite familiar with Kubernetes, but before that, I'm going to get into telling you a little bit about what our infrastructure looked like before, and what we were doing with it, and then why we decided to move this. So Cloud 66 is delivered as a SaaS. As you can imagine, we, as a company that's 4 or 5 years old, we had this stack all set up on AWS, running on EC2, S3, the normal, the usual suspects of the cloud. And this was delivered, our service was delivered as a service on the web when you go to cloud66.com. This was working perfectly fine. We had a very good record of uptime. We had a track record of delivering around probably 2 or 3 times a day on minor releases and once a week on major releases. So we had a good flow of everything that was going on. And we decided to move this to Kubernetes for different reasons. So this is what our stack used to look like. Now, the reason there are so many colors in this is deliberate. I necessarily didn't want to try and see what color combinations I can use. It's to show how many different server types we had on our stack. So at the top, you have the usual ALB, ELB load balancers that Amazon provides you. And then at the bottom, you have the type of service that we had. At the very bottom of the lower square or rectangle, we have the databases and the persistent storage services that we had. So MySQL, Redis, Memcached, InfluxDB, and RabbitMQ are the persistent or services that we provide and we use within the application. But with the application stack itself, we had 5 or 6 different types of servers that we had to provision every time. So we had a bunch of web servers for obvious reasons, where they were serving 3 types of traffic: the web API and our admin API, which is something that we use internally through a VPN for administration purposes. Think of it as a kind of management network. Then we provide Git services to our customers. So there was a Git server, or a cluster of Git servers, I should say. We collect metrics and vital signs of the servers that we manage for our customers. So there's metric servers. We have a bunch of services that communicate over TCP. So they're not traditional, layer 7 web HTTP servers, and those are used for various different purposes. I boxed all of them into one TCP. In the real world, the box on the top right, the TCP server, in reality, it's actually about 3 or 4 different types of server. And then we have a bunch of background server workers. So as you can see, we had all these different types of servers that we had, each one being an EC2 template that we would fire up. We would scale them from that type. And the first issue that we had around this was about something of an issue of like a collective picture that you can take, and the images where that had that issue. The first issue was that we would take these images of a worker. So for example, we would build a worker server, and then we would take a picture of it, essentially take a snapshot of the template, an AMI in Amazon lingo. So we can fire up another worker server later on. And by the time we were firing it up, that image was already out of date. Either we've updated something, or an upstream package was updated, or there was a security vulnerability found in it. So our job ended up being updating those images. Now, admittedly, we don't have hundreds of types of servers and 100 types of images as a consequence, but still, that was a painful process. The other thing was that although we have good discipline around taking care of our infrastructure in a reproducible way, in infrastructure as code or script, if you will, we oftentimes find ourselves, because of an issue, because of a routing network issue, for example, on the cloud provider or one of our customers, we had to jump on a server and make a quick fix during the weekend just to get production back up and running, or solve a specific customer's problem. And that meant the images that we would take and the templates of those servers would diverge from the original image that we'd taken. And when we fire up another one, we had to apply that fix until we get to the next cycle of embedding that change, that manual change, into the original image. And the last problem that we had, which came about quite recently, was that we started selling Cloud 66 as an on-prem service as well. So until then, we were providing our service as an online available service in one package. Cloud66.com was the place that we would sell our services. About 6 months ago, we started providing Cloud 66 as an on-prem, which meant we had to build the entire stack again at different locations, depending on where the customer wanted or which data center on the cloud they wanted it to be. And that added to the problem. So we thought about this, and then we, as a company that provides containerization and Kubernetes services, naturally we had to move our own stack to run on Kubernetes as well. So this is what we wanted to build. Ideally, this is what we wanted to build. We wanted to have all uniform nodes doing whatever the containers inside them will do, but from outside they will look the same. There is no taking of images. We have different types of load balancers depending on the traffic type, whether it's level 4, level 5, level 4, level 7, and different ones. And hopefully we'll have everything in there, including MySQL and Memcached and everything else that's there. So that was the ideal stack that we wanted to build. We set out to build this. The first challenge that we had was around databases and persistent storage in general. The first realization we had around databases was that while we deploy our code about maybe 3-4 times a day, we wanted to ideally do it more often. The last time we deployed our database, as in bumped up the version, for example, or changed anything around our database, was pretty much never. Maybe a year before that, maybe even 18 months before that. So the frequency of change in a database in terms of the database itself, not the schema and not the data itself, but the database engine itself and the code was completely out of sync. It's as out of sync as 3-4 times a day versus once every 18 months. So one of the biggest advantages of containerization for us was not necessarily applicable to databases. The other advantage of having containerized backend was stability and high availability for our application, where the container that would serve your application would potentially can run anywhere, and therefore would be something that is when it runs, if there's an issue with the underlying server, it can be moved somewhere else. With databases, we would benefit from that, but realistically, we were running our databases on Amazon RDS or other database or infrastructure as a service, essentially components that were provided to us. So we were not getting that much of a mileage out of using databases in containers, but we still tried to experiment with that. The biggest issue that we found was, while we had good practices around making sure our schema is backward compatible and we don't ever break our application with a database change, and we could keep that, the entire containerization of a database did not really fit well with our deployment strategy. We had to technically say some of our databases, some of our containers which contain databases are special, and they are different from the rest of them. We wanted to avoid that as much as possible. We set out to do this to make sure that none of the servers are special. All of them are uniform. And all of a sudden, we had to treat some of the containers now as a special. And by special, I mean they shouldn't be deployed every time, because you want your database to be always up to date, always up. They preferably couldn't move even with the best storage underneath. There were hiccups around access to database when the container providing the database moves from one node to another. So we had to pin them down, which means that then you have a single point of failure. So the first thing that we realized is that we're not going to take our databases into containers. We left them outside, and we still carried on using the database part. And I'm using the word database in a general way for anything persistent and stateful, including RabbitMQ, for example. And we kept them outside as services provided. The second part that we found challenging were around secrets. So traditionally, what we do is we put the secrets around, credentials to database access or API keys to any service that our application use. We would put them inside the configuration of application. Now, that is encrypted and it's not committed into the Git repository. It's coming from outside. We had something very similar to HashiCorp's Vault, for example, built a long time ago. We called it Secret Service. And what it does is that it provides secrets to the application in a short time window when the application starts up. And we wanted to move that over to Kubernetes Vault and use it. But we also wanted to use Kubernetes native secret management, the config maps and secrets. And what that meant was that we had to put our secrets into Kubernetes configuration files and commit them into Git. Now, you might say you don't have to commit those files into Git repositories, or you can commit them into a Git repository, but they can be encrypted. Now, if you look at a configuration file for Kubernetes for secrets, you see that it is a key value pair, essentially. The key is the secret name, the value is an encrypted or unencrypted value for the secret. And in theory, we could have left those files outside of our version control. But the issue with that is, first of all, it's not ideal. Then you have to store it somewhere because obviously you do. And the second part is usually secrets and applications work in lockstep. When you have a new API service that you start using, you want to add the secrets to it. Add the API keys to the secrets file at the same time, and you want those to go out at the same time without disrupting your service. So we had to have them in some sort of source code repository, even if it was not the main source code repository of our application. And that meant how the issues that we had with that was around what we're going to do with access right to Git. What if somebody just commits the secrets in plain text into the Git repository by mistake, forgets to encrypt them? We experimented with other services like GitCrypt, for example, which works around and making sure all the files of a certain type are always encrypted. But we found them restricted in terms of they have a binary access control. Either you have access to all the files that are using GitCrypt, or you have access to none of them, which meant we couldn't distinguish between secrets for our test environment and secrets for our production environment. And clearly, within the developer team, and especially now with GDPR, that we need to know exactly who's got access with what, we needed to know. We needed to make sure that production secrets are only accessible to very few, while staging and test environments potentially have access, are accessed by more people. So the Git-based encrypted secret management files solutions didn't really work for us. Another thing was we wanted the concept of a write-only access. We realized that that's actually a necessary thing for us to have. And by that, what I mean is, as a developer, if I go and add a new service, or I want to make a change to, for example, the way one of my services consumes a secret, I might want to be able to add this new service and add the secrets that I want into the right place, which is the Kubernetes secret file. But necessarily, I don't need to have, or shouldn't have, access to the actual secrets themselves. So it ended up being something like a write-only access, where I can modify the secret files as to add a new one or redirect the secret from another place, while I don't have access to seeing the secrets themselves or what other secrets are available for me to see, even if they are encrypted. And that was a challenge for us. Another concept that we started to kind of struggle with were environments. Now, all of us as software developers are familiar with environments like staging, like test QA, production. But one of the things that started to show up quite often for us was the fact that we ended up firing up the entire stack on Kubernetes with the same environment multiple times. An example is if you have a SaaS business like us and you want to start selling it on-prem, then what is the difference in terms of the environment between your SaaS version and the one that you sell to your customer on-prem? They could both be production. So now you have two production environments, but they have different configurations. For example, the endpoints that they get things from or the API keys that they use are potentially different. They're not going to share the same secrets, same endpoints, same configuration parameters of your SaaS. So you have two production environments with different configuration files. Or alternatively, you might have a case of wanting to have multiple stagings based on different branches or different features that you add. And environments don't cut it anymore there either. What you end up with is you have these environments that are fired up, and then you'd have to have tiny variations between the configurations. While the majority of the configuration is the same, there are some very minute variations between specifics of the configuration that are different. We experimented with another environment called on-prem, which was equal to production in every other sense, and it had its own slight configuration changes. But then as we started selling Cloud 66 on-prem more to more customers with slight variations or slight customizations, that started to kind of go out of whack as well. So we realized that we need another thing, we need another concept on top of environment, something that is more like a deployment destination. And the last challenge we had to overcome was around configurations. Traditionally, pretty much everyone puts the configuration next to the code and in some sort of a file, whether it's a params file or a JSON or YAML of some sort. And we wanted to use the Kubernetes native way of config maps and pull it out into Kubernetes to manage those configurations for us per namespace, if you will. But we realized that we needed that to be either repeated in multiple namespaces or shared. And by that, what I mean is, if you think about each Kubernetes namespace holding one instance of your application, then you can think of configuration of that namespace, of that instance, being config maps within that namespace. So you have one namespace that holds your code and also your configuration as config maps. And you have another namespace that's another version of your application, or another, for now, let's call it still environment of your application, and you have the configuration for it there. And then you have a lot of repeats. So if you go and have to do a code rotate, like an API key rotation, because either it's compromised or as best practices, you want to rotate the API keys to your, for example, I don't know, AWS API, you have to go around every single one of those namespaces, every single instance of your of your application, and do the key rotation over there. Obviously, there are solutions around that, but we wanted to use the native Kubernetes way, and that was another challenge. So we started working on our CI/CD pipeline to solve those problems, to see how we can embed our CI/CD, these things into our CI/CD CI/CD pipeline that we have. We were using a normal, CI/CD solution that would just take our code from the Git repository, run the tests, and then deploy it. And we found that very difficult to adapt that solution for what we wanted. It would do the CI/CD kind of traditional things like your own unit test and integration test very well, but then we wanted to have blue, green, or canary deployments, or be easy to roll back in production, or do things like don't pull images from Docker Hub. Make sure that you pull it from our own repositories. Make sure that there are no developer adds tag latest, for example, to the images, or do image scans for known security vulnerabilities or bad base images, and all those things. Obviously, when I look at something, for example, like Jenkins as an open source CI/CD solution, I look at it as a bash file. I look at it as a scripting language that I can do whatever I want to do with it, and I can find a plugin or write a plugin for it, and it will work fine. But ideally, we wanted something that was built specific for these requirements around containerization, around solution around environments, with a solution around secrets and configuration. So this is what we ended up building. All those problems led to this being our pipeline, and we called it a container delivery pipeline. As a result of this, we released the product and we open source a bunch of it, which we can I can tell you about a little bit more in detail. And hopefully you will find those open source solutions useful. But on the top left, we would get the code from source code from a Git repository, or potentially some pre-built Docker images. Now, the pre-built Docker images on the top left, they could either be one off-the-shelf Docker image, like Redis, for example, the official Redis image, or it could be an artifact of our pre-existing CI/CD solution that we have. So if we have Jenkins, for example, that takes our code and builds it into an image as an artifact of this, the test, and it puts it into a Docker registry, we can pull it from there. Either way, the first step for us was to make sure the code is tested and make sure that every deployment is tagged with the same uniform tag across the board, whether the image comes from off-the-shelf Redis or it's something that is our application and we build it. And that's what this retagging and building steps are. So we built that step, the building and retagging, as the first step to make sure that we have a snapshot of our application, including the code, configuration, environment variables, and everything else that's there. The result of this effort was one open source project called Habitus, which you can see here, and it supports build steps where you can take one part of the code, build it into a bunch of Docker images, and then take those images into the next step. And also it supports other things around providing secrets during build files, where you want to have, for example, a private Git repository during your build, potentially for private dependencies within your application, or squash the images, take the secrets out, take layers out for security and vulnerability test purposes. It does all of that, and then it tags everything at one step. So now that we have a snapshot of the code, configuration, everything in one file, then we can put it into a container registry. Now, our solution worked with our own registry, but we do support other ones as well, because we wanted to, when we go to an on-prem solution to sell it to an on-prem customer, they might have a different container registry, so we had to support that. The next step for us was asset management, and this was an interesting part that we it was a late realization after a bunch of production issues that we had that we needed. And by annotations, I mean, ideally what we wanted was to go into a kube control pod, describe pod, certain pod, and know exactly which Git commit was used to build this. When was it built? Who built it? So we can track it back and see where it's gone, where it is. And all those annotations, we wanted those to be available to the code and application itself, so it can be used in the log files. That will allow us to trace one request from outside, from the web, all the way back through the log files to see where it's been through the entire flow. Now, as you can imagine, because we are not every traffic type that we have is HTTP, we have TCP traffic, it wasn't quite possible for us, and it is about a year ago, to use a service mesh completely in that sense that we could benefit from a service mesh to trace traffic. So we had to make sure that the metadata is available to the code, so it can be used to augment the logs that are written by the application. And that's the first step that we do after the images are registered. So all the images are tagged and registered, as well as that all the assets that are resources that are deployed to Kubernetes are tagged. We also do scanning of the images. We wanted to make sure that there is no security vulnerability, no base image vulnerabilities available there. Integration testing is a byproduct of that, the next step. When we have all the images, including databases in this case, for integration test purposes, inside of containers, we could just scaffold the entire stack up and then run some integration tests around it. The configuration challenge we overcome with a hybrid solution with Helm. So Helm is a great tool when it comes to off-the-shelf installation of applications. We looked at it as a potentially a software delivery solution where we could have the best practices installation of RabbitMQ with a single command of Helm. But what we found it lacking was that we couldn't dictate, or we couldn't specify policies around for developers. So when they create new services in Kubernetes, how those services should look like. Now, to give you an example, if we wanted to make sure that any developer who adds a new, say, ingress to our Kubernetes follows a certain criteria. They always have to get this TLS certificate from a specific place. They always have to annotate it with these annotations. They always have to call it a certain way, and they have to have it in a separate file named such. And all those things that can be applied to it. While we could go to our ops team and ask them to write Helm charts, or get the developers to write Helm charts and get them to be validated by someone else, we prefer to have the native Kubernetes resources written as guidelines, as templates, and now, as we call it, stencils, for each one of those resource types. So now what we ended up with is, for off-the-shelf tools like RabbitMQ, right, like our Memcached, we use Helm. But as guideline for any new development within our application, with our own application, we use stencils, and I can show you what stencils look like. After that, another thing that we found quite useful was being able to have access to upstream native Kubernetes API without having a wrapper around it. Now, this kind of goes back to this entire analogy of Kubernetes being a vending machine, and our applications being candy inside of that vending machine. We wanted developers to have access to stack up the vending machine with their applications, and external vendors to also stack up the vending machine with the apps. We also wanted to give access to the entire API of this vending machine, or for example, Kubernetes in this case, so they can benefit from the upstream Kubernetes, have the community around Kubernetes, and the entire CNCF community around it, so they can use the internet, find answers on Stack Overflow around the issues that they have, without us restricting access to that Kubernetes API to avoid mistakes being made. An example of that was an example around the load balancers. So the load balancers that we have, the level 7 load balancers that we have fixed IP address, a global fixed IP address on Google. And we wanted to make sure that those then get changed. We could have locked it out. There could be like an RBAC policy around it, but we couldn't enforce those policies around the file names, for example. File name of a configuration for Kubernetes is completely invisible to Kubernetes when you apply that. So we open sourced another project called Copper, which the entire promise of it is to act like a unit test for your Kubernetes configuration files, with a simple DSL that you can say things like, if the IP address for the load balancer is changed, let me know. It doesn't necessarily mean it's a bad thing. The deployment has to stop, but somebody has to sign it off. Or you can say things like, if somebody is using latest as a tag for a Docker image, then deployment will stop. And that's an open source project that we rolled out as well as a result. Deployment workflows are the next step. So we wanted to, this is kind of a normal thing in the CI/CD when you have multiple steps of rolling out to staging and into production, et cetera, et cetera. So that's one. And then with manual approvals around each one of them. So another team member has to sign it off. And then formations, which is our concept that we came up with when we had issues with environments. So formations here are versus environments. So environments are independent of deployment. It's just an environment. They are limited to the number of environments that you have, like production, staging, and QA, and that's pretty much it. And you usually have some sort of undocumented meaning. Production, when you say production environment, everybody kind of says, oh, make sure that you don't break anything. And staging is kind of like, oh, it's kind of ready to go to production, maybe you're testing it. But these things are it's not necessarily a convention or written anywhere. We wanted that to be more structured. When we say production, we mean certain things. And also we wanted to have multiple sets of production environments, on-prem, off-prem, dedicated on the cloud or our SaaS. And that's the concept of formation for us. So we created this concept called formations, and we deploy to formations, not to environments. Formations are like a deployment target. You can have as many formations as you want. And each formation can have an environment. You can have a formation that is running on GKE and it's production, and you can have another formation that is also production, but it's running on AWS. for various different reasons. You might have different formations for different features, for different environments, for different clients, for different customers, for different geographic regions. And when it comes to stencils versus like normal templates like Helm charts, for example, version control on that is an optional thing. If you have a chart repository, you don't necessarily have version control. If you opt in not to, we wanted to have structured around that, make sure that our configuration files are version controlled. We didn't want to allow people to use flow control inside of YAML. For example, something like, for every service loop, and then middle of it, somebody would go and add, if service name is front end, then there is a difference. That would just make the entire configuration file not very understandable, not maintainable. And templates are kind of domain independent. They are sometimes the same language, templating language is used for rendering HTML. But we wanted to have something that's aware of the fact that it's rendering the YAML file for containers, for Kubernetes, essentially some sort of a DSL. So we built a stencils with version control, with support for base templates, so you can get something like base of a deployment, and then expand that yourself into what your deployment looks like. For it to be domain specific, i.e., I'm building the result of this template rendering is a Kubernetes configuration, and have a simple markup instead of having flow controls, if then else, for loops, whiles, and things like that. So Habitus is the first open source project that we rolled out around this. It supports multi-step Docker builds, and it does support multi-servers, so you can roll it out on multiple servers, and each step can be built on different server in your farm. It is multi-tenanted as well. So you can have multiple builds running of the same thing, of different versions of the same thing, and it doesn't mess up Docker daemon. It also is cache aware, so it knows which part needs to be built where. You can find it on habitus.io. And it also just does support secrets during the build, where if you have an NPM or a Ruby gem or a Go library that is a private repository and it needs a private SSH key, it does support providing that during the build and then without leaving any traces. And Copper, as I mentioned, it allows you to have your developers to have access to vanilla upstream APIs. It can stop the build as opposed to just warning you and asking for an extra pair of eyes to sign off the deployment flow based on various different conditions that could happen. And you can have extra asset policies like file names and folders, as well as intra-asset policies where you can say things like some assets should have annotations, or some assets should be, some IP address of an asset should be within a specific range. At the end, our stack ended up looking like this. So we kept our databases inside of our database as a service, or RabbitMQ as a service providers. And now we have a pool of nodes that are identical. They are read-only OS as well. So we cannot even make changes to those deliberately. So that's a good thing. And we can fire up new ones, and shut down old ones with rotating upgrades and all the things that comes with it. Now I want to show you Copper specifically, if I may. Just as a quick. So this is Copper that you can see here around Copper SH. And if I show you some examples of how it works, it's a command line tool that you can run. And the example, for example, example of not using a latest tag as an image, it kind of looks like this. I can write a rule, and this rule exists in a file. You can call it a cop file. And I just fetch any image under my containers. And if you're familiar with Kubernetes, deployment resource, you know that the image of a Docker image that's used inside of a pod is defined under images of containers of template spec. So this is kind of a JSON path, XJSON path, if you want, way of addressing the image. We take that. Copper understands the concepts like the Docker image, So it looks at it as a Docker image, which means if the tag is non-existent, it knows it's latest. If the repository or registry is non-existent, it knows it's Docker Hub. It picks up the tag and it makes sure that it's not latest. Or things like, you want to allow your developers to bump up your MySQL version if you're running it inside of a container, only by minor versions, not major versions. And you can do things like this. So you can get the image name of any MySQL, use it as a tag, pick the tag, and it understands semantic versioning. So you can look at it as a semantic version and make sure it satisfies this version control. Extra asset policies, you can do things like make sure that the extension is YAML, not YAML, if that's what you want. If the kind of an asset, which you're familiar with, this is a Kubernetes concept. If the kind is a deployment, then the metadata name, in the metadata name, then the file name should end with deployments, and obviously the extension is YAML. So if that's a you can think of it as a policy that you can enforce. Again, it understands IP addresses, for example, so you can have things like my load balance IP address should be within this range. No Docker Hub images is another one that you can think of, or you can enforce things that you always pull the images from a private registry and not the public registry. You can enforce all those things. So it's a very powerful DSL with very simple syntax that allows you to enforce policies that would allow your developers in turn access the upstream native Kubernetes API without restricting them and without you having to check every time manually that any of their policies or compliance things are broken. So with that, I wanted to thank you for your time. If any questions, I would love to answer that about what we've built and what we've open sourced. We turned this entire pipeline into a product. We call it Cloud 66 SkyCap as a result of that. And where we are now, our uptime stayed pretty much the same as before, but our scaling and our scaling and also being able to move from one region to another has become much faster. Our on-prem deployments are pretty much instantaneous now, and our deployments are more predictable and repeatable as a result. And other things that we can do with this new setup is that we can deploy a minimal setup somewhere onto a cloud, onto a Kubernetes stack and cluster. And then in case of an issue, we can augment that deployment, replace the pods with more debug-friendly pods where they do log shipping and other things, and we can get at that. And we can do all of this with this concept of formations. So we have formations that are production, but other formations are production log friendly in another way. So that's a kind of a brief, very quick rundown of what we had to build to move our workload over to Kubernetes. And thank you very much for your time.
Thank you, Cash. So we have around 20 minutes for your questions, so feel free to drop them in the Q&A tab in the webinar interface, and we are happy to answer them. Before we're waiting for another questions, probably as you may highlight some roadmap on your projects that you have just highlighted for us, and some further steps and other notable items that have not been covered by this presentation.
Sure. So on the Habitus side, which we didn't really I didn't really go into details of. So Habitus is a build workflow tool for Docker files. On the Habitus side, we are working with Microsoft specifically to integrate that into Draft, which is a continuous build solution for development where we can build using your local Docker daemon, but also multi-step builds using your Docker daemon and Habitus. So that's one side of it. On the Copper side, because Copper is not necessarily when Copper works, it loads your configuration file into a JSON format, and every rule and every policy that you write for it is applied to that JSON in memory format. That means you can load pretty much any file format, any file type into Copper and add validations for it. As a result, with Copper, what we can do is we are going to open it up to other non-Kubernetes configuration files for any configuration system. It could be Helm charts that you could validate, and it could be non-Kubernetes configuration related things for any others, for example, CNCF open source projects that has a configuration file, whether it's YAML, JSON, TOML, or anything else. We can do that. So that's on the roadmap for us to extend the reach of Copper into more configuration validation for non-Kubernetes specific things, and extend this DSL to understand the concepts of things like Helm charts, for example. So that's the immediate roadmap around those two projects. As for Cloud 6's SkyCap, rolling it out for more customers and seeing the use cases they have and how we can take care of more traditional CI/CD workloads as well as specific deployments to production is where we are going to. So for us, CI/CD tools that are out there are very, very good solutions for building and testing containerized infrastructure. But our aim is to make SkyCap the ultimate Kubernetes deployment tool when it comes to a microservice-based application.
Perfect. So we're still waiting for your questions. Otherwise, we may save around 15 minutes of your time. So it's just a call for attendees. Right, so I'm counting to 3 and we are closing this webinar. So 1, 2, 3, that was the final call for the questions here. Thank you, Cash. Thank you, everybody who has joined us here today. Just a reminder that we are holding the CNCF regular webinars every Tuesday, exactly this time, depending on which time zone you're allocated. So also this webinar has been recorded and will be available in the next few days on the cncf.io website. Thank you for joining us today and goodbye.